welcome everyone to this AAC&U webinar on how to transform your math class into a thinking classroom experience. We are so glad that you are here with us and decided to join us this afternoon. I am Patrice Moss. I will be your moderator for today's webinar. Throughout the year, AAC&U serves as a catalyst and facilitator for innovations that improve educational quality and equity and support the success of all students. We focus on evidence-based strategies that elevate high-impact teaching and learning experiences and that prioritize capacity-building efforts to achieve higher levels of student success and engagement. Today's webinar is just one of the many resources we provide to that end. We are so grateful to our program partner on today's webinar, Maplesoft. Their generous support enables us to offer today's content for free, and we thank them for both their financial and intellectual contributions to today's webinar. Participants, we welcome your engagement throughout the session. You can use the Q&A option at the bottom of your screen to pose questions to our panelists throughout the session. We'll also leave time at the end of today to address many of your questions. In addition, you can use the chat function to seek additional technical support or to engage with the other attendees. Due to the size of the audience today, we probably won't get to everyone's questions live during the webinar, but please know that you can also join the ongoing conversation on social media via X, Facebook, or LinkedIn. So with us today, we have Karishma Pumwani, Director of Product Management of the Academic Market at Maplesoft. She will be joined by our 4 fantastic panelists. Alexandre Cavalcante, Assistant Professor, Ontario Institute for Studies and Education, Director of the Center for Science, Mathematics, and Technology Education, University of Toronto. Lancelot Gooden, Provost, Osceola and Poinciana campuses, Valencia College, Orlando, Florida. Scot Gould, Professor of Physics, Scripps College, Pitzer College, and Claremont McKenna College. And Susan Palmberg, mathematics teacher, Edwin O. Smith High School, Stores, Connecticut. At this time, I'm going to turn it over to Karishma, who will introduce our colleagues and frame this exciting conversation.
Thank you so much, Patrice. At this point, I'd like to ask Alex to join me so I can ask him a few questions. Alex,
Hello.
Thank you so much for joining me today. So I want to kickstart this presentation. We have a lot to dig into, but with the first question here. So Alex, you're a strong advocate for the Thinking Classroom framework and other frameworks like this. Can you start by explaining what this framework is and why it's so transformative for students?
Sure. Hello, everyone. Nice to meet you all. And I'm really thankful for Maplesoft and AAC&U for this opportunity. The Building Thinking Classroom framework is actually a framework that has been provided and constructed by Peter Liljedahl, who is a professor at Simon Fraser University here in Canada. It's a framework that has been really going viral in North America and across the world, really, on how to teach mathematics in a way that engages students and puts them at the very center of the learning experience. It's actually a comprehensive method that really reflects decades of research on active learning. So as you might hear a little bit from me as I describe this method, it actually reflects a lot of things that many of you might already be implementing in your classroom, but the actually effectiveness of this framework is that it sort of encompasses all of this that has been going on for quite a while in education. So the Thinking Classroom framework flips the traditional order of teaching mathematics, which is traditionally the teacher presents certain content, students and teacher work together on some activities to make sense of the concept, and then students do things individually at the end of the learning process. Through the Thinking Classroom framework, all of this is flipped, and students start the learning process by exploring in smaller groups. And particularly, there are 3 main characteristics of this framework. One is that students work in vertical surfaces on their whiteboards or on flip chart paper in very small groups that are visibly random in the classroom. So they work in these small groups, making sense of problems that are thinly sliced. So these kinds of problems, they are presented to the students by changing only one variable on each problem. So they start making sense, for example, from moving from linear functions to polynomials or quadratic functions. And it's been really transformative, I would say, because the uptake has been tremendous across North America and even in other countries across the world.
Thank you for that, Alex. I appreciate it. Would you be able to share with the audience today some specific elements of the Thinking Classroom framework that you found particularly transformative in your experience?
Sure. By the way, I'm putting here in the chat a link for the official website of the Thinking Classroom framework. As you will see, there has been a lot of social media and resources being created around this framework. So there's a lot of support and support that is free and accessible to every level of education. To me, particularly, this framework has been transformative and powerful because it gives an instructor, it gives a mathematics teacher a comprehensive and systematic approach to constructivist student-centered teaching. You know, many times when we go into conferences or when we pursue professional development, we hear those big words in mathematics education, we hear all of these new ideas, but sometimes it's hard to really think about how do I change my classroom to reflect that kind of thinking, that kind of philosophy. So the Thinking Classroom framework provides 14 teaching practices that you can start from day one. You can start with 1, 2, or 3 of these practices and really build your support around convincing other instructors and participating in social media. I also think it's particularly helpful because it reframes the role of the teacher. You know, I'm pretty sure many of our colleagues, our participants here today have been math teachers and instructors for many, many years. And we see that for many of these teachers, the passion for teaching seems to go down over time because of the challenges that we face in our classrooms with the world, with new challenges and problems that emerge, especially after the pandemic. So from what I've noticed, teachers that try this new approach, they tell me, and they tell social media and researchers how much of their passion has been reignited. And these are teachers who are working in remote classrooms. These are teachers that are working with English language learners. These are teachers that have big struggles with the demographics and the composition of their classrooms, but they notice so much change in the engagement of their students.
Right. Kind of shifting gears a little bit, I know one of your roles at OISE is really to educate or help math teachers, develop the skills and the tools they need when they go out into the classroom. So can you talk to me a little bit about why you make it a point to introduce math teachers to different technologies in your course? What is it about these tools that you find transformative?
Right. Full disclosure, when I was learning mathematics myself as a student in high school or even in university, I didn't have a lot of technologies, right? So I learned calculus in the same way that most of the participants here learned calculus, by doing things on paper, on the whiteboard. But we have to recognize that the world is different. The way our students do mathematics, even the way mathematicians do mathematics by themselves, is different nowadays, right? So I make a point to introduce technology to my teacher candidates, to teachers in the field, because we need to recognize that the way we reason, the way we think about mathematics has also changed. And this is not unique to the last decade or so. Historically, mathematics has been developing knowledge based on the tools that are available at that period, right?
Right.
So if we have these technologies that nowadays allow us to represent mathematics more dynamically, do math problems in ways that take away some of the cognitive load from our shoulders, why not approach mathematics in this way? But then we have to adjust the way we're doing things, right? So for me, introducing technology is really a way to show my students, to show teachers that we can focus on what really matters. Many folks here are probably teaching in college or university settings, So we need to understand that students come with different procedural gaps from their own experiences. When we use technology, we can sort of bridge these gaps and focus on the conceptual content that we actually need to teach at that course, whether it be calculus, differential equations, or linear algebra.
Thank you so much for sharing those answers with me, Alex. I really appreciate it. At this time, I'd like to bring Scot Gould onto the scene so I can ask him a few questions. Scot, thank you so much for joining us today. So Scot, you're known for using Maple extensively in your physics courses. Let's start more broadly. Why do you believe software is essential in teaching, especially in subjects like physics?
Well, most of my interest in terms of the mathematics is it is a tool, it is a language, it is a series of rules that I use for me to explain principles. Physics is the study of fundamental physical properties and principles of the universe. I mean, what we traditionally called laws. And of course, we also understand these things through real world systems. So in the thinking classroom, I can start the class by saying, here's a real world situation. What do we make of this? Can we go beyond of, well, this is what happened, being descriptive? Can we make predictions? And this is where software comes into play, in that we can be able to look at a system which is much more realistic. It's not filled with spherical cows, and be able to study a much more realistic system. So again, fly balls in the outfield are not in a vacuum. We want to include error resistance. We want to be able to reproduce what we see on TV and make predictions. A lot, particularly for my students, I'm not here to teach algebra. My goal is for them to spend time thinking about principles and let the software do a lot of the mathematical minutia that goes on in solving the problems.
Great. So Scot, let me ask you, how has the use of software transformed your approach to teaching physics?
Well, for my students, by using software to model both realistic and that is non-synthetic and systems and reduce the amount of mathematics, I am able to spend more time on the conceptual understanding. There's evidence that students from a wider range of academic backgrounds can learn physics principles and their applications better if we emphasize concepts and reduce the use of mathematical representation. And this is completely opposite about how physics has traditionally been taught. In fact, I'm looking at the intro textbook just now, and again, it's the beginning of let's memorize a bunch of equations, and that's not about physics. Physics is about understanding principles. So once the concepts are well understood, then we can go back and do the mathematical, start working on the mathematics. And again, using software to do a lot. I mean, we allow calculators in a class.
Right.
What's the difference between adding that and things to be able to do computer algebra or calculus for us?
Fair enough. So one last question, Scot. I think it's very daunting for educators to select the right software for their class. So what should they consider when selecting software for their students? Are there specific features or capabilities that they should look for?
Okay, thank you for letting me bring a slide in. So if I could, I sent you a slide, and if you could show this slide. And the big deal here is you got to get student buy-in, okay? So we need to be able to get a situation where students can generate their own content. Remember, we learn by doing, not by watching a demonstration. So the reason I've used Maple is primarily or one of the majors is that the Maple math, what they put into is the written math they see in their textbooks. So there's less of a communication. You don't have to learn a new language. I can also solve these symbolically rather than just one specific example. I certainly want to make sure, and this is one of the things I had to learn was I spent working on lots of different other systems, Python, MATLAB, Fortran, math. And I want minimal coding. I want them to do the most with the least amount of activation barrier in learning. I certainly want them to get immediate feedback. That's it's not just, well, I'm going to scribble something on the page and then just turn it in, and I don't know what happens to it. Particularly for me, it was important is that while there are many physics simulators, PHET is a fantastic one at the University of Colorado. A lot of them are black box, but if they can see the equations that they're working with, that both on the screen and on their paper, it's easier for them to make the connection of, oh, this is why my model actually produces the results that I'm seeing in this graph or in this black box. So again, the key is once I do that, I can go on and introduce concepts that are well beyond what the mathematics skills are of most of the students are entering. Most of my students enter with ability to do calculus, but if they understand a derivative and they understand an integral, I can teach them how to use Maple to solve linked differential equations, which is essentially how we do modern mechanics and physics.
Awesome. Thank you for sharing that, Scott. I appreciate it. I'm glad you got to use your slide. Scott, at this point, I want to turn it over to Lance. I have a few questions over here for Lance. Lance, thank you so much for joining our webinar today. So Lance, I want to start off. You began your 2019 Maple Conference talk with this quote, and I love the quote. It said, "Technology will not replace great teachers, but technology in the hands of great teachers can be transformational." Can you explain why you chose this quote and what it means to you?
Absolutely, Karishma. I'll start by saying that I fundamentally believe that teaching has an irreplaceable human element, such as motivating students and providing emotional and social support that, to my knowledge, technology has not replicated today. I heard this quote by George Couros on his podcast, The Inventor's Mindset. I chose the quote as a reminder that transformative learning for students in a mathematics class using technology begins with the instructor. In my Maple 2019 talk, I shared examples and testimonials from math faculty and students at Johnston Community College who shared the tremendous impact integrating technology such as Maple in their math classroom that it has on instruction and student learning. So the faculty, they effectively leverage technology to amplify their teaching, making learning math more relevant, less intimidating for students, a more efficient classroom, enjoyable, interactive, essentially creating a thinking classroom. Having integrated technology in my math instruction for over 2 decades, and specifically Maple for a decade in my college math classes, I've realized the faculty role in use and energy and excitement is essential for that transformative learning experience, not just in the hands of students and say, do it. So what this quote means to me is that when technology integration is combined with the pedagogical expertise of our faculty and their content knowledge, it creates a powerful synergy, allowing our educators to enhance learning in ways that transcend traditional teaching methods.
I love it. I love it. So my next question is, how did you actually go about incorporating software into your calculus teaching? And how did that change your approach? And what was your students' experience like?
Well, absolutely. It's been phenomenal and exciting. Introducing difficult topics, especially in our calc courses, it's very difficult without technology. With the technology such as Maple, it was really easy. Complex concepts became very simple to introduce. I was able to design more exploratory and project-based experiences using Maple to assess students' learning at what I consider key momentum points in my calculus courses. Day-to-day instruction became less routinized, allowing students to experiment and explore and more deep concepts to really deepen their conceptual understanding of the mathematics. I have a video demonstration to show one of my favorite momentum points in Calculus 1 to really help students better understand the computation of limits. So in this particular demonstration, it shows the computation of limits analytically, numerically, and graphically. So using this Maple limit tutor as we scroll through the application, it will show the stepped out procedure for computing limits. Scary for math instructors. That is quite fine. We're not quite there yet. We want them to understand what exactly they're doing. We're not just plugging the number, getting an answer, because there are some intricacies with studying points of discontinuity. But using the analytical tutor, we scroll to like a numerical approach using the table values. Well, one can study limits intuitively or numerically by examining the left-handed and right-handed portions of a limit. So from the left-hand side, as x becomes sufficiently small, you can see that the function value decreases to approximately 3. And this is something that's, students can able to explore on their own. But from the right-hand side, they also realize that as x becomes sufficiently small, the function value, in this case, increases to approximately 3. So that's some form of convergence that is occurring. But then what's a more interesting part is the graphical component. As you scroll, you realize that Maple is able to create an animation. And what you see is that students can then visually see how we trace the x-axis from the left, and that's the red arrow, and trace the curve from the left. It's decreasing to that circle, which is a point of discontinuity on the graph. And essentially from the right, they can do the same. And it's a very simple way for them to realize, well, the limit as x approaches -1 of this function is really more dynamic concept than one that's concrete and very easy to determine that the value in this case is 3. Thank you.
Yeah, I love this. Thank you for sharing this video and kind of walking us through this. One of the things that I think is unique, and I'd like to ask another question, just because we've talked about it so much, is, you've successfully convinced your faculty to adopt software. What strategies did you use to overcome resistance and to get them on board?
Well, I learned from my mistakes because, it wasn't my first try, and I learned not to try to implement technology at scale on my own. So the strategy one is to better understand the faculty resistance to adopting technology. And through my experiences, I've recognized there are essentially 6 key reasons. 1, time and trust, risk, quality of instruction, support, and value. I'll just say a few. So for time, faculty often perceive learning new technology or integrating technology in their courses to be time consuming, and it is. However, you can save time because instead of doing repetitive tasks or really reteaching concepts, students really gain conceptual understanding much sooner with the integration and effective use of technology. Trust is one where faculty fear the use of technology, in this case, such as Maple. And often the concern is that it returns solutions that leads to misconceptions. Very hard to reteach those or undo those. So, what I would say is really share more success stories from many of our expert users and really provide data-driven evidence of how effective this has been for students. And lastly, I'll just share one more in terms of support. Professional development is key. And I know that what was phenomenal is really the Maple support staff that really engage with our faculty and reassure them that they're able to provide the support they need to learn the technology and to be able to implement this effectively in their classrooms.
Awesome. Thank you, Lance. And one last question. I know we're short on time, but you've also emphasized the importance of technological literacy. And can you talk about how software helps in this area and perhaps share an example? And it's the example that I'm really excited if you could share it with our audience over here.
Oh, absolutely. So in my Calculus 3 course, or just assessing our students that we usually do, I recognize a high proportion of my students, they were aspiring transfer students into mechanical engineering, electrical or biological engineering fields. So, for example, distinguishing between what's considered an orientable or non-orientable surfaces to solve problems is really critical to understanding the divergence theorem and Green's theorem in Calculus 3. Another key momentum point in my course. So it was really neat for students to apply the knowledge of parametric surfaces and use a computer-aided design software to really convert what was a function to what's called a stereolithography file and create a 3D print. Well, this is a surface that's orientable, a torus. However, with the Maple was able to create the STL file or stereolithography file and export to a slicing software in a 3D printer, slice it, and then it creates a locked-in or interlocking Mobius strip in 3D form. So imagine this solid in the hands of students and the kinds of conversations they can have now about orientable surfaces, non-orientable surfaces, and what it means for a unit normal vector.
I love that. I wish I was taking calculus with you way back when. Thank you, Lance. I want to now turn it over to Sue, and I have a few questions to ask her. Sue, thank you for joining us today. So you've been a longtime advocate for using technology in the math classroom. What do you see as the biggest benefit of integrating software into your teaching practice, particularly when it comes to enhancing student understanding and engagement?
Yes, thank you. So as a teacher, I've always been excited about technology and how I can integrate what's new into my lessons. So from graphing calculators, augmented reality, virtual reality, all different kinds of software. So I believe that this excitement is contagious. I try to inspire my students to embrace the technology, and hopefully they share that same enthusiasm. So integrating technology into my teaching practices offers significant benefits, particularly in enhancing student understanding and engagement. For example, software like MapleLearn can allow students to see interactive simulations and visualizations, making abstract concepts more concrete, just like Lance showed. For example, in calculus, we can also look at dynamic graphs. They can help students see immediate effects of changing variables without having on paper and pencil draw graph after graph after graph. It's kind of instantaneous. Also in my calculus classes, especially for when I do solids of revolution, it's hard for students to see how to take a region and rotate it around an axis, where something in MapleLearn can be done instantaneously. Also, I think it's fun. You know, I've always thought technology was fun. So interactive tools, gamified learning experiences, multimedia resources, they capture the student's attention more effectively than any kind of traditional method. So engaging software can make learning more enjoyable, and it motivates students to participate and become more active. One thing I'm really excited about in my classroom is I recently won a grant from my school to purchase virtual reality headsets. I'm going to be using them in my multivariable calculus class to show 3D graphs. So, you know, another thing that just get really excited about, and hopefully the students get really excited about it too.
Yeah. So one question is, you know, you're an advocate for using realistic examples and meaningful problems to motivate your students. You've done a lot of activities and you've already mentioned a few of them. Can you help share some more of the activities that you give to these students and how it's helped to increase their motivation and engagement in math?
Exactly, sure. So like you said, I'm a very strong advocate for using realistic examples and meaningful problems. They definitely motivate my students in math. One activity I give my students involves designing a glass. So they start by creating a piecewise function. They'll rotate that around to the x-axis, for example, and it will form a shape of a glass. So using MapleLearn, they're able to adjust their original graph to perfect their design. Then the software can, like I said, rotate their image, and it creates that 3D model of their glass in real time, like they can see it right there. Afterwards, however, the students will calculate the volume of, say, the material they would need to make the glass, and then the volume of water that can hold the glass. This project sparks creativity and competition, really, in my classroom. Students are working hard to create the most unique and functional glass. One year, I even had students that designed the Stanley Cup, and it came out pretty good.
Wow.
Yeah, another example I have students design a dam. And for that one, I have students that are given specific parameters for the task to design the dam. They calculate the amount of material required, estimated the cost of construction. They're all doing this all on Maple. These realistic problems they highly motivate my students. I even had former students reach back out to me after they graduated and say that these examples help them when they were in their college engineering classes, because they had that connection between the math and the engineering.
Yeah.
So definitely linking math to real world, the students gain that deeper appreciation for the subject, and they become more invested, which is awesome.
Absolutely. It's tangible, something that they can touch and feel. In fact, you have to work with Lance and now get them 3D printed and get their glasses 3D printed. Yeah.
I think we're going to have to talk after this is over.
Perfect. So one last question, and I know this is on everyone's mind, so I'm gonna have you ask or answer the toughest question, which is, there's often concern that educational software might make it too easy for students to cheat or bypass traditional learning methods. How do you address these concerns, and what safeguards or practices do you implement to ensure that technology enhances rather than diminishes learning?
Well, it is a tough one. Not a year goes by that I, come up with a student that will cheat by using technology. So what I try to do is I focus on the learning process rather than just the final answer. So for example, when using software like Maple Learn, I require students to document steps, explain their reasoning, reflect on patterns that they might observe. This approach ensures that they're actively engaging with the material rather than just simply relying on it to do the work for them.
Right.
Also, in terms of the Building Thinking Classroom, I arrange my students in small random form groups each day. I encourage them to collaborate and discuss. So this peer interaction helps students learn from each other. They ask questions, they explore different approaches. So it makes it harder to say cheat because their emphasis is on more group learning and collaborative problem solving. Another thing, if I can add, is while I do have students using the software to facilitate that exploration and that discovery, I also require students to apply the traditional methods, such as manually proving their hypothesis that they might make. And that blend, I feel, just ensures that students develop that strong foundation of understanding, along with their ability to use that technology effectively.
Awesome. Thank you so much, Susan. At this point, I want to call all of the panelists, kind of have them up on the screen, and I want to ask everybody one last final question, same question to everyone. So here's the question. As we wrap up, what's one practical piece of advice you would give to educators who want to start implementing these ideas in their classroom tomorrow? And what's the first step they should take? And I'll go ahead and start with you, Alex.
All right. So just to connect with what the other panelists have been saying, you've all heard comments about how they use technology in their classrooms, right? But you didn't hear things about them lecturing, presenting. Rather, I heard many times the panelists talking about they have students do this, they have students do that, they have students build things. This is truly the spirit behind the Thinking Classroom framework. And traditionally, if you read the books, if you engage with people on social media, you will see that not a lot of them talk about the role of technology in those classes. So I think that's primarily the benefit of this webinar today, is to start thinking about how mathematical software can have a role in this kind of classroom. The advice that I would give you is actually basically three. The first one is participate in social media groups. It's really hard to try to engage with the new framework without having a community of support, without having the experience of other people that are also doing that. And Facebook, particularly, as well as Twitter or X, are very, very powerful tools because people are actually building resources and sharing them for free. Another one is make the expectations to your students very, very clear. These are students who have been doing mathematics for 12, 13 years of their life in one way, and then they come to your class, hopefully, they will face and engage with mathematics in a completely different way. They might have some sort of resistance because that's something different to them. So really make it clear what is the point and what are your goals in implementing this new approach. And the third one is, this is an investment. You're gonna have to have patience. You cannot wait. You cannot expect to implement today, and by tomorrow your students are the biggest thinkers in your class. it's going to take a little bit of time for them to get used, but you will see the results. But you have to trust and invest and put the effort and wait a little bit for the culture of the classroom to actually change.
Thank you, Alex. I'll go to Scott now.
Let's see. I guess, yes, you have to make an investment. I probably would also say, because I spent a lot of time with a lot of free software, and because I had a value that I knew to do real physics problems, and the way physicists do real physics problems is we use a computer. So why am I teaching in my classes ways we don't actually do science? So that's probably the biggest, and mathematicians use computers all the time as well. There was a comment about, is this an infomercial for Maple? And I'll tell you that that's fine. Karishma knows that I have made many suggestions in the past about how Maple could be improved. If there were something better, I'm sure, and then I do use other approaches as well. But I would say certainly one thing is, don't be willing to invest in a lot of money upfront, because if you end up with saying, I'm going to take the thing that's free or what other people have used, but their resources are really difficult to implement and the students don't give you buy-in, then that costs you more than if you spent money upfront.
Thanks, Scott. Yes, and you do have a list of feature requests that you want, which we're slowly working through. So I appreciate that. Lance, I'll pass it on to you.
Yes, thank you, Karishma. I don't have as many requests as Scott, but yes, you from using Maple 9 until now, yes, it has evolved, and certainly there continuous room for improvement. But I would say that the technology that we experience in our day-to-day life cannot be independent of the experiences in the classroom. The advancements in technology, as we know, and innovations, they are ubiquitous across our industry and in our daily lives. And this has transformed the work, the way we communicate and learn. So a math classroom absent of really relevant technology today, that's not really good for students' learning experiences and the ability to adapt to the technologies and the advancements in the world today. I would say our advice, start small, integrate the technology gradually, through your lessons. If you go full force, you'll have more roadblocks than not. And choose specific topics, the graphical features, not just Maple, there are many others, and I've used quite a bit, and Karishma knows this as well. But there's so much out there. But the reality is that you're using technology efficiently and effectively in your classroom. And lastly, I'll say that from a learning community, at Valencia College, a growing number of math faculty have formed learning communities engaging in high impact practices to institutionalize Peter Liljedahl's framework in their math course instructional design. These communities, from what was shared with me, that they foster a culture of continuous improvement, support among faculty, and strive for student-centered learning in mathematics.
Awesome. Yes, thank you. I feel like there's recurring themes from all of the answers. I'm sure Sue will have her own spin on it. Sue, how would you answer that question?
It's very similar. So I would say my practical advice is to begin with activities that are already well established. You don't need to reinvent the wheel. Start by trying out one of the activities that are going to be shared with this webinar. Or, I use Maple Learn, so visit the Maple Learn site, search for an activity related to the concept that you're teaching tomorrow. Then I would say, you got to trust yourself, but hand it over to your students and let them figure it out. That's the key, not to have all the answers, allow your students to work together collaboratively, explore, discover the solutions without you providing the answers or step-by-step instructions. This approach really fosters that independent thinking, encourages problem solving, ultimately leads to that deeper understanding of the material. So I guess the first step is to simply trust in the process and let your students take the lead in their learning.
I love it. I think that's a great way to end this segment, and I'll kind of pass it back to Patrice, who I think is going to moderate the Q&A session for us. Patrice.
Yes, thank you, Karishma, and to all the panelists for all that juicy information. So I hope you all were able to take some good takeaways and some key points from the conversation. So now we're going to jump into Q&A. And the first question that I have. One second. I'm sorry, my apologies for that. The first question is to Alex. You mentioned that we need to focus on asking better questions in math education. Could you elaborate on what you mean by that and how it ties into the use of technology?
Sure. I want to take everyone back maybe 100 years or maybe just 50 years. 100 years ago, there was, if you went to high school at the time, not that anyone here was 100 years old, but if you could take a time machine and go back in time, there wouldn't be a mathematics class. Mathematics didn't exist as one single subject in schools. There would be geometry, algebra, and arithmetics. So the invention of mathematics as a school subject is a fairly recent phenomenon, especially after set theory became the sort of agglutination of everything in mathematics. Regardless, historically, there has been this perception in mathematics teaching that mathematics is a subject that accumulates over time, and you cannot take one step before a previous step. So you depend on certain procedural knowledge, certain procedural fluency to then bring your students to understand a higher level concept or a more difficult concept. But in fact, this doesn't exist because that's the nature of things. It was because of our technological limitations. Nowadays, we can ask conceptual questions to students before they develop certain procedural fluencies, because now we can represent certain mathematical concepts. We can represent and make dynamic visualizations of algebra, calculus, geometric properties of certain objects. So there is, in a way, a change in how we can approach certain ideas in mathematics. We can start with the endpoint and then develop alongside with the students their understanding of that concept. So if we have this way of reasoning that's now faster nowadays because of technology, why not focus specifically on those deep conceptual questions, just like Scott mentioned in physics? Just very quickly, two examples that I would give you is related to differential equations or linear algebra. So when you solve differential equations, students spend such a long time learning the techniques to solve them, but not as much time thinking about what a differential equation does, what kind of modeling is actually happening. And I remember when I was teaching, and as well as when I was a student, I would be lost myself in the middle of the process of solving, that I had lost completely the train of thought of why I came up with that differential equation in the first place. The second example, in linear algebra, we focus so much on teaching about how to operate with matrices, but not as much time thinking about what is the point of using eigenvalues or eigenvectors, for example, to operate with power of matrices. So we can start with the endpoint in justifying and really discussing with the students the point of what they're doing, and then use technology to really fast track the procedure that they might develop in other classes or even in our classes, but that's not the fundamental goal of our teaching. So for me, that's the importance of technology in asking better questions. It helps us keep focus on what we want to solve or what we want to learn.
Thank you, Alex. The next question is directed towards Scott. What should educators consider when selecting software for their students? Are there specific features or capabilities they should look for?
Yeah, I'd say there are three things I look for. One, does it actually demonstrate or do what you're asking you would want the students to be able to accomplish? 2 is the activation barrier. That's a chemistry term, sorry, is the amount of time it's going to take them to learn to be able to solve this problem low. And then 3, is it expandable? Can you essentially, does the software allow you to go beyond just solving the one problem that you wanted to be able to solve? Then it is useful. So again, it's got to be functional. It's got to be easily understandable, because that's the student buy-in. The students don't buy in. It doesn't matter what we do. And then finally, is it expandable? And once you do that, then I found that it is easier to do these ideas of essentially the flipped of the classroom, of me going blah, 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 and then they working. I still do some of that, but more now I can do, okay, we've done some of these ideas here. And if you want, you can refer to videos, and here's the problem we have to solve.
Thank you, Scott. Our next question is for Lance. What do you say to those who are concerned that software which can show steps may encourage cheating? How do you dispel this misconception?
Thank you for the question, Patrice. I would first begin by saying that a thinking classroom makes cheating irrelevant. So design your class in such a way that it is a thinking classroom. A classroom that reinforces learning. One of the things that Alex mentioned is, that about students starting with the end. I think about, what concepts in calculus. Students study extrema a lot, but in calculus 3, extrema on a multivariate surface is very complex and very difficult to conceptualize. So using software like Maple, you can generate that kind of image to show them a rectangular boundary, which creates a prism that projects upwards, intersects the surface. And I'm trying to think about listeners visualizing that, right? But that's already projected onto a screen, and students can see that, and they can rotate the image and tell the extrema on the vertices, the extrema on the traces, and the extrema on the surface on the inside. But seeing that, it doesn't make the 50 to 100 steps as daunting, because often it will take that many steps to arrive at the solution. So it's really important to think about how you're designing your class to reinforce learning, because students already come to our classrooms in mathematics with so much fear. We've heard students and adults say, I am bad at math. That is not cool. So to then, impose the idea that you're cheating by using a technology that's accessible to you, whether it's Maple, Photomath, and Maple has the Maple calculator companion app where they can take a picture of the actual problem and upload to the cloud feature. These are things that you want to teach them to use. These are 21st century skills for students. We can reframe our questions by asking the questions differently, focused on the why the method works, and move beyond route calculation, as Peter in his book mentioned, mimicking. We do that a lot. I have done it. And that's not deep thinking happening in mathematics. Think about, why is a function continuous on a given interval and not differentiable, as opposed to solving 100 problems with different derivative techniques. My favorite, and the last I'll share, is a multiple integral. Well, if you can solve a multiple integral by showing all the steps, whether it's rectangular form, cylindrical form, or spherical form, why not change the order of integration? Have them rewrite the integral in 6 different ways. And then you see something interesting of how they realize what the definite integral means for a solid. So there are many ways to reframe the question to deepen their conceptual understanding of what they're actually doing, as opposed to mimicking problems on a board.
Yes, and I also
Can I jump in
addressing-
for just 1 second?
Sure, go ahead.
Because Lance just spoke to me. All as physics professors, one of the things he says, a lot of our students come to class and they can do double and triple and integrals that we have no idea how to do anymore. But they don't understand what it means, and they don't know how to set it up. And so it's just, all they've done is be program. They haven't thought about what the mathematics means. All right, sorry, I'm off.
Oh, no. Thank you, Scott, for that contribution. I was just saying I wanted to also thank Lance for defining cheat. I know that was a conversation that was going on in the chat, so I hope that his explanation gave some clarity to that. So our next question is for Sue. Sue, how easy is it to get your student to adopt the technology that you mentioned in your talk? Don't you think that the time dedicated to adopt the technology should be dedicated to learning the math instead?
Well, I can say that my students can pick up, they seem to pick up technology very easily. In terms of the different technologies that I use, whether it's graphing calculator. Today I did an activity using a motion detector with a graphing calculator, and they were on it. They really enjoy that technology. And I think that the second part of the question was the time dedicated or invested in that, I think is tremendous in terms of the reward you get for them understanding the math instead. So in terms of learning the technology, maybe there are some students that have a difficult time on the technology, but the students are working together and they all help each other out. And I like to just stand back and just watch them do it, because it really is amazing how they help each other out. And then in turn, they're learning more of the concepts. It just makes it a lot easier, because now we don't have to spend a lot of the time on the nitty-gritty. The technology will just get it there for them. And they see the patterns, they understand the material, and I see it. It's just amazing.
Thank you, Susan. Our next question is for Alex. As a part of the thinking classroom, the teacher acts as a facilitator rather than a traditional lecturer. So what is the role of the technology?
Right. For me, there are two particular roles that technology could play in the thinking classroom. The first one is, I don't like the word, but the tool aspect of a technology, right? So when students are doing their works on vertical surfaces individually in their small groups, and the teacher goes around and facilitates that whole conversation and the solution to those problems, we have to understand, and this is really hard sometimes for us as teachers to let it go, we have to understand that students are free to explore and try things out by themselves. They can figure out the methods to solve those problems in a variety of ways. Of course, as you move on to higher education, perhaps certain classes are focused on particular methods that are important for them to learn, but there are other moments in which the students can explore the methods freely. And using technology can help them grasp the problem first, to then figure out what possible approaches to solve the problems they could have. So I would imagine, for example, technology being almost like a complement to the whiteboard in which students are working vertically, so they can visualize and display the problems in certain ways to then solve them in their small groups. But there's another role that technology might play, and I know there was a question about whether this was an information from MapleSoft, but I don't know any other software that does this, so I will mention that. MapleLearn can really help students in one of the parts of this thinking classroom framework that is called Check Your Understanding. So yes, students are working on their vertical surfaces and exploring problems freely, but there is a moment in which students will sit down, they will reflect individually and take the notes that they find appropriate for that topic in class. So there is still a moment for taking notes and really solidifying your understanding. And MapleLearn particularly, I don't know any other software that does that. I would be happy to know, and if people have that information. But on MapleLearn, students can create their own notebooks of notations and thinking that is also dynamic. It doesn't need to be a traditional notebook in which students try to recreate the graphs and the representations they created previously. They can actually create those dynamic representations and have them saved for their own notations, for their own notebooks. So in summary, technology can have these two different roles in the thinking classroom framework. But I will say that research on this area is really, really recent. People that have developed the thinking classroom framework haven't really considered the role of technology in that. So there's still a lot of research to be done to think systematically about that question.
Thank you, Alex. Our next question is back to you, Sue. The participant wants to know, what about exams? How do you structure them?
Okay, so I actually structure them a couple of ways. I have two sets of or two parts of an exam, for example. One part, the student would have access to technology. Mainly in high school, we use graphing calculators. So I would allow them to use graphing calculators to answer questions where they would specifically need the graphing calculator. So the questions that would have to be asked in such a way so that the graphing calculators could be helpful for them to use. And then the other part of the exam where I want to see whether they understand and can manipulate what they need to in terms of the problems by hand. Do they know the concepts? Can they apply them, etc.? That kind of thing. I do teach in a high school, so my students do take the AP exam. And in the AP exam, part of the questions are calculator based, where they do have access, and parts are non-calculator based. So that's your basic exam. Since I do randomly put groups of students in groups, there are some times that I give them group assessments. So the students would have to work together to come up with the solutions. Usually what I do is I would set up groups, say for whatever the concept happens to be. At the beginning of the week, they would work through with those same groups. So they're working together very well. As I monitor them working together, and then their assessment would be such that they can help each other, and their assessment would be a group grade. They would all get the same grade for that assessment.
Thank you, Susan. Well, I think that we are coming up on time. Thank you for all the questions that were asked, and thank you to our panelists for answering them in great detail. So before we go, there is, before we wrap up, we wanted to know how this webinar has influenced your approach to using technology in your classroom. So take a short minute just to answer the poll that you see on your screen so we can just see how the perspectives have shifted. All right, well, it looks like, you know, that a lot of you are planning, have already used, are looking to expand, and that is great. For those of you who are in this space where you're trying to learn more and infuse more technology into your classrooms, that leads us right into our next part of our webinar, which is how you can do that, how you can get more information. So we actually hope that you have really enjoyed this webinar and found the insights on transforming your classroom into a thinking classroom valuable. If you want to learn more, if you're interested in getting some resources and additional information, please scan that QR code that's on your screen right now. It'll take you directly to some MapleSoft activities and resources. Additionally, consider joining us at the MapleSoft User Conference, which is virtual and free. And it will take place in October, October 24th through 25th. This is a great opportunity to connect with other educators and see how they are using the technology to transform their classrooms. If you can't attend live, that's okay. Register anyway, because then you will have access to the recordings of all the sessions. We also recommend you attending the AAC&U Transforming STEM Higher Education Conference in November. That's November 7th through the 9th. This key event focuses on advancing STEM education reform, sharing innovations, and fostering community and transformation. And MapleSoft will be present at this conference. Thank you again and again for participating, and we look forward to seeing you at these upcoming events. I hope everyone has a great rest of their day.